Just take a quick look at the schedule here and see where we're at. Today's the 22nd day of February. We're rapidly approaching the mid part of the semester here. So we're about halfway done. Anyway, 6.3, I will open up the chapter 6 quiz on Alex. That'll be due by midnight, February 25th. The Alex chapter 6 homework will be due by midnight, February 24th. I'll open up 6.3 if I haven't already opened that up. It will be opened up promptly after the session. The chapter 5 and 6 exam on Alex will also be opened up. That'll be due midnight, February 28th. So just keep those dates in mind so that you don't fall behind. Okay.
Yeah, and if I'm not mistaken, 6.2 isn't open up yet either.
All right. Well, I'll make sure that 6.2 and 6.3 is opened up. Okay. All right. So those are dates worth remembering, ladies and gentlemen. Just keep those in your pocket. Okay. All right. So section 6.3. I'm not going to go through this PowerPoint in its entirety. I will post a PowerPoint on Canvas along with the video, of course. But I'm going to go over the first, I think, 7 slides here to get us started. The rectangular coordinate system. Sometimes it's called the Cartesian coordinate plane, or sometimes it's just referred to as the plane. All right, and we're going to work with linear equations in 2 variables. And we'll show you how to represent all of their ordered pair solutions in the XY plane. Hopefully, by the time we get done with this section, we will know how to plot points in the XY plane, graph linear equations, find the X and Y intercepts of linear equations, determine the slope of a line, graph linear equations in a very special form called slope-intercept form, be able to graph a horizontal or vertical line, and recognize their equations. And finally, but last but by no means least, in fact, I think it's the most important aspect of this whole investigation, is applying linear equations to the real world. Okay. All right, so ladies and gentlemen, this is the XY plane. Notice it has a horizontal number line, which oftentimes, but not always, is referred to as the x-axis. It has a vertical number line that is perpendicular to the x-axis. This vertical number line oftentimes, but not always, is referred to as the y-axis. Notice we have evenly spaced tick marks on each of the axes. And for this particular XY plane, they are spaced 1 unit apart on both axes here. If we go to the right, we go in the positive x direction. If we go to the left, we go in the negative x direction. Upwards is in the positive y direction, and downwards is in the negative y direction. Together, these axes basically partition my plane, my paper, up into 4 quadrants. Quadrant number 1, 2, 3, and 4. Okay. The intersection point of these 2 axes has a very special name. It's called the origin of the XY plane. You can kind of think of it as being like this XY plane was made possible by having an explosion originate at the origin. Okay.
Yeah. I think it should just be like a light blue, because I have the kind of.
What's up? What's wrong?
Well, like we just leave a shade of light.
All right. So this is called the XY plane. It has a lot of names depending upon what book you look at. Sometimes it's referred to as the Cartesian coordinate plane, the rectangular coordinate system. Sometimes it's just called the plane. All right. All right, so plotting points in the XY plane. To plot points, we always start at the origin, and then we move, according to the X and Y coordinates of an ordered pair. So ordered pairs are always going to look like this, with parentheses. The first entry of the ordered pair is called the X coordinate. The second entry after the comma is called the Y coordinate of the ordered pair. Together, these coordinates determine the location of the point in the XY plane. All right, so if I have the ordered pair 2, 5, I would start at the origin and I would move 2 units along the positive x-axis. Then I would move up 5 units parallel to the y-axis. 1, 2, 3, 4, 5. And then we would plot the point 2, 5, which is in quadrant number 1, correct? All right, let's plot the point -5, -4, starting at the origin. I go 5 units in the negative direction along the x-axis. Then I go down 4 units parallel to the y-axis, -1, -2, -3, -4, -4, -3, -4. So 5 to the left on the x-axis, down 4 parallel to the y-axis, and we land at this point, -5, -4, which is in the third quadrant. Any questions how those points have been plotted there so far? All righty, here's another example of the XY plane and points that have been plotted in it. 5, -3, start at the origin. You go 5 along the negative x-axis, and then you go down 2 units parallel to the y-axis. And wait a minute, I went the wrong way. 5, -3, the x-coordinate is +5. So we start at the origin, we go 5 units to the right on the x-axis, and then we go down 3 units, -1, -2, -3 units parallel to the y-axis, and that point would be found in the fourth quadrant. 0, 4, notice the x-coordinate is 0. That means we do not move off of the y-axis. We stay right on the y-axis, and we just move up 4 positive units. 1, 2, 3, 4. 0, 4 is a
You paid $300 last year. I just pay the rest. I just send the rest to her.
Okay, somebody does not have their mute button
Yeah.
on. They're holding a conversation.
You had ended up sending it to me, the 300, and I had ended up, she had ended up buying some here.
Okay. All right, so these points have been plotted in the XY plane. -2, 0 has a y coordinate of 0, which means we do not move off the x-axis. We just move 2 units to the left on the x-axis and plot the point, -2, 0. Any questions how these points are being plotted in the XY plane? Any questions? Sometimes you may not have nice coordinates for your ordered pair. You might have like, maybe like fractions or decimals. So if you had the point 1.5, -0.7, how would you plot this ordered pair? Well, you just have to be a little bit more careful and just do the best you can. So starting at the origin, we move 1.5 units along the positive x-axis. 1, and then 1.5 is dead center between 1 and 2. Then we move down -7/10. -7/10 is just shy of -1. And so 1.5 -7/10 would be probably right about there in the fourth quadrant. Any questions on our plotting points here? Okay. All right, what would be the ordered pair address of point C, which is in the second quadrant? Well, to determine the x-coordinate, we just project this point perpendicularly down to the x-axis, and we strike -3. Therefore, its x-coordinate would be -3. To find the y-coordinate of this point, we project it horizontally back to the y-axis, and we strike the tick mark 4. So this point C would have the unique ordered pair address of -3, 4. Questions, how we're plotting points in the XY plane? All righty. And here's just some more points that have been plotted in the plane. Notice the scaling on the y-axis has the tick mark spaced 2 units apart, not 1 unit apart. So, and on the x-axis, they're still spaced 1 unit apart. Make sure that you pay attention to the scaling that's being used on your axes. There's nothing sacred about tick marks being 1 unit apart. For instance, on my x-axis, I could have my tick mark spaced 500 units apart, 500, 1,000, 1,500, 2,000, 2,500, negative 500, negative 1,000, negative 1,500, et cetera, et cetera. It just depends what kind of data you collect in the field as to what type of scaling you're going to need to represent the ordered pairs. All right, but nonetheless, these axes are linear axes. So if two tick marks on the horizontal axis are spaced 1 unit apart, then that means all tick marks must be 1 unit apart. If two tick marks on the vertical axis are spaced 1,000 units apart, all of the tick marks on the y-axis must be 1,000 units apart. So they are linear axes. Okay. All right, done with that. And like I said, that PowerPoint presentation will be posted on Canvas in its entirety there. All right, so we learn how to plot points. Big deal. Another thing we're going to learn how to do, ladies and gentlemen, is we're going to start working with what are called linear equations in 2 variables. Not 1 variable, but 2 variables. And in general, these linear equations look like this. Where A, B, and C are just any real numbers, X and Y are the variables. Because X and Y are raised to the first power, we call this a linear equation in X and Y. A linear equation. Solutions to such an equation are not just single numbers. They are always going to be ordered pairs. They must be ordered pairs. Let's look at a specific example. Suppose I give ourselves this linear equation to play around with. 2x plus 3y equals 5. And I ask myself this question: is the ordered pair 1, 1 a solution to this linear equation? Well, to be a solution to a linear equation, an ordered pair has to satisfy the equation, which means that when we replace the x variable with the x coordinate, in this case 1, and replace the y variable with the y coordinate, in this case 1, we better get a true statement. So is 2 times 1 plus 3 times 1 equal to 5? Is that true or false? Well, this does give you 5 on the left side, and 5 does equal 5. So the answer is yes. 1, 1 is an ordered pair solution to that linear equation. It satisfies the equation. Let's try another one. Is 2, 4 a solution? To find out, we replace the x variable with the x coordinate of 2. The y variable gets replaced with the y coordinate of 4. And then we ask ourselves, is this a true or false statement? 2 times 2 is 4. 3 times 4 is 12. Is 4 plus 12 equal to 5? The answer is no. So 2, 4 is not a solution to this linear equation. Can anybody think of an ordered pair solution to this linear equation? I've given you 1, 1, 1. Is there any others? Or maybe this is it. Maybe this linear equation only has 1 ordered pair solution. I don't know. Can anybody think of another possible solution? I think I can think of maybe another one. How about this one? Is negative 8, 7 a solution? Replacing x with negative 8 and y with 7 in the equation. Let's find out. Is the 2 times negative 8 plus 3 times 7, is that equal to 5? Is negative 16 plus 21 equal to 5? It is, isn't it? So the answer is yes. We have found yet another ordered pair solution to my linear equation here, negative 8, 7. It satisfies the equation. Can anybody think of any other ordered pair that might be a solution to this linear equation? Or maybe that's it. Maybe it only has two ordered pair solutions. Any other one that might exist? Oh, look at this one. How about 5 halves 0? Is 5 halves 0 a solution to this linear equation, as messy as it is? To find out, I replace the x variable with the x coordinate of 5 halves. The y variable gets replaced with the y coordinate of 0. Now, 2 times 5 halves is 2 over 1 times 5 halves, which is 10 over 2. 3 times 0 is 0. Is this a true statement? 10 halves happens to reduce down to 5. Ah, I found another solution. I found another ordered pair solution, 5 halves, comma 0. So we now have uncovered 3 ordered pair solutions to this linear equation. Do you think there's any more? Can anybody think of another possible solution to this linear equation? Anybody? Or maybe that's it. Maybe there's only 3.
What about 15/3 0?
15/3 0. Replace the x coordinate, the x variable with 15/3. Replace y with 0. Does this equal 5? 15/3 is 5, and 2 times 5 is what?
10.
10. 10 plus 0 is 10. And unfortunately, 10 does not equal 5. No, it doesn't look like that would be an ordered pair solution. But hey, kudos to you for at least trying. Okay. You might think of another possibility. It might be an ordered pair solution. Or maybe does this thing only have 3 solutions? I don't know. Beginning to wonder. Anybody come up with maybe another solution? Well, let's see.
20 over 10, 1.
20 over 10 and 1. Let's try it out. 20 tenths and 1. Replace x with 20 tenths. Replace y with 1. And let's see if this works. 20 divided by 10 is 2. And 2 times 2 is what? 4. 4 plus 3, does that equal 5?
No.
No, it doesn't. All right. Almost, but it just didn't work, but at least we tried. Okay, I'm gonna try one. How about the ordered pair 10, comma, -5? Maybe that's an ordered pair solution. Let's try it out. Replace x with 10. Replace y with -5. And does the left side equal 5? This is going to be 20. 3 times -5 is -15. Well, I'll be darned. We found another ordered pair solution. 10 -5 is an ordered pair solution to that linear equation. So now we've uncovered 4 solutions. What are you beginning to think here, ladies and gentlemen? Do you think there's only 4 ordered pair solutions? Seems like every time we think that there's no other solutions, another one seems to surface. Anybody want to go out on a limb and predict how many solutions this linear equation does have?
Has infinite amount of solutions.
You are correct. It has an infinite number of ordered pair solutions. We have just found a pithy 4 solutions. There's an infinite number of other possible solutions. Now, how am I gonna sit here and list all infinite solutions? I would be here till the end of time, or death, or until the cows come home. Do you agree? And we don't have that time. So we can't sit here and list an infinite number of solutions. We'll show you how to represent where the infinite number of solutions belong in the XY plane when we learn how to graph this linear equation in the XY plane. But we're not there yet. We're getting there. All right, ladies and gentlemen, so let's try it out. What did I say? What was that key word? Graph. What does it mean to graph a linear equation in the XY plane? Well, since these linear equations have an infinite number of ordered pair solutions, the only way to represent, okay, where they do lie in the XY plane is to graph the linear equation. By graphing the linear equation, that indicates where all the infinite ordered pair solutions must be in the XY plane. Now, this is a linear equation. And in the word linear is embedded what word? In the word linear, we
Line.
see the word line embedded in the word linear. Line. That's there for a reason. Because here's a well-known fact. The graph of any linear equation, EQN is short for the word equation, in two variables, the graph of any linear equation in two variables is always a line in the XY plane. It's always a line. Now, if you stay in this math business long enough, you'll start working with nonlinear equations where maybe x is raised to the second power, or maybe raised to a fractional power or negative power, in which case those graphs are not line graphs, they're some sort of a curve type graph. But we're just going to work with linear equations today, okay? There's many ways to graph a linear equation in the XY plane. We're going to first of all look at what's called the table method. This is a popular initial method that is portrayed in all early algebra books. As the name suggests, we make a table. My first column is going to be called the X column. My second column is going to be called my equation column. My third column is going to be called my Y column. And my fourth column is going to be entitled my ordered pair column, X comma Y. Now here's how it works. Ladies and gentlemen, we can choose any numeric value for X, but whatever we choose for X, we must substitute it into the equation for the X variable and then solve for Y. Because we can choose any real number value for X, you might want to keep your choices nice and simple. You don't want to do something silly like this. Why would you want to choose X to be 1 million? Do you agree it's going to be very difficult to plot a point whose X coordinate is 1 million? That's not happening. You could do this, but why? Suppose you wanted X to be 171 over negative 119. Do you care to work with something that nasty looking? You could do that, but why? You don't need to. Let's choose nice values of X. Nice values of X might be like -1 or 0 or 1 or 2. Keep the values close to the origin so that you can plot the points. All right, if X is -1, let's find out what Y has to be according to this equation. Y has to be equal to -1 plus 4, which is to say Y must be 3, which is to say that we've generated an ordered pair solution to this linear equation, namely -1, 3. We've generated a solution. Suppose X is 0. Put 0 in for X. Y must be equal to 0 plus 4 then, or equal to 4. So we have another ordered pair solution, 0, 4. Let X be +1. Put 1 in for X into the equation and solve for Y. Y must be 1 plus 4 or 5. Hence, we have another ordered pair solution of 1, 5. Let x be 2. Put 2 into the linear equation in for x. Y therefore must be equal to 2 plus 4, which is 6. Hence, we have another ordered pair solution of 2, 6. I have a question. Bare minimum, how many points or solutions do we have to generate for a linear equation to determine its unique line graph in the xy plane? How
Is
many
it 3?
points? How many points bare minimum can you get away with to determine a unique line in the plane? Bare minimum, 2 points are needed. That's all you need, bare minimum. If you can, ladies and gentlemen, come up with 2 ordered pair solutions, 2 unique ordered pair solutions of a linear equation, all you gotta do is put a line through them, and you'll have the unique line graph for the linear equation. 1 point's not good enough, because 1 point through 1 point, you can put an infinite number of lines. Infinite number. There's an infinite number of lines you can put through 1 point. Right? So 1 point is not good enough to determine a unique line. You need at least 2 points. Now, if we're sloppy, we may need 3 points if we want our graph to look accurate. For instance, if you're sloppy, ladies, I'm putting the line through 2 points, you could get in trouble. By the way, always use a ruler to put a line through points. You could be sloppy and do something like this. Or you could be sloppy and do something like this. Now, it doesn't look like these lines are the same line. Do you agree? Looks like they have radically different slants or slopes to them. So if you're going to go with 2 points, just make sure you put the line through the center of both points. Through the center. Then you'll have an accurate graph, okay? To avoid this possible confusion or problem, 3 points are better than 2 points because it eliminates this possibility here. 3 points. But 2 are bare minimum requirement. Do I have enough ordered pair solutions to y equals x plus 4 to graph this equation in the xy plane? What do you think? Yes or no?
Yes.
We got more than enough. So what I do is I get my hands on some handy dandy, what kind of paper is this called?
Graph paper?
Graphing paper, that's right. And I'll attach a sheet of this on Canvas and you can print it off and make copies of it. But it's really cool because it affords you per sheet two graphs, 2 separate graphs here, okay? Always label your axes. This is my x-axis, this is my y-axis. Very important, always label your axes. I will assume that these tick marks are spaced 1 unit apart on the x and the y-axis. All right. You can label a couple of them to establish the scaling that's being used. And now we have to plot these ordered pair solutions. So how do I plot -1, 3? I start at the origin and I go 1 to the left, then up 3. 1, 2, 3. There's -1, 3 in the second quadrant. Now you don't have to do this, but if you want to, you can label the points if you want. It does clutter your graph up, okay? There's -1, 3. Now I want to plot the other solution I found, which was 0, 4. Plot 0, 4, we start at the origin, we stay on the y-axis and move up 4. 1, 2, 3, 4. There's 0, 4. Now I'm going to plot the other ordered pair solution, which is 1, 5. Starting at the origin, I move 1 to the right, then up 5. 1, 2, 3, 4, 5. There's 1, 5. Finally, I'll plot the last solution I generated, which is 2, 6. Start at the origin, 2 to the right, up 6. 1, 2, 3, 4, 5, 6. Ladies and gentlemen, you be the judge. Does it appear that these points lie on a line?
Yes.
We would say these points are collinear points. Collinear, meaning that they lie on a line. Take a ruler and put a line through the center of all these points. And now this is very important. Make sure you put an arrow at the ends of your line. Ladies and gentlemen, that line represents the graph of the linear equation y equals x plus 4. We have just graphed this linear equation. It's this line. And any point that sits on this line would be a solution to this linear equation. So I have a question for you. How many points could I put on this line?
Infinite.
Infinite, because this line goes on forever in both directions. You got some solutions to this linear equation which are really nasty, messy solutions, which would be too difficult to even accurately read off their x and y coordinates. Do you agree it'd be difficult to accurately determine what the x and y coordinate is of this point right here? But nonetheless, how do I know it's still a solution to y equals x plus 4? How do I know this is still a solution? Because it lies on the what?
Line.
It lies on the graph of that linear equation. And any point that lies on this line would be a solution to that linear equation. Some solutions are nice solutions, like these are, the ones we found and plotted. But some of them fall in between tick mark values and are really nasty to read off the coordinates for. But nonetheless, they are solutions still to that linear equation. So this linear equation has some nice ordered pair solutions, and it has some extremely messy ordered pair solutions. Okay? But there are an infinite number of them. Any questions how we graph y equals x plus 4 using the table method? All right, so ladies and gentlemen, I understand that you don't have any graphing paper on you, and that's understandable. But let's see if you can, just be accurate enough and maybe drawing an XY plane and maybe evenly spacing some tick marks on both axes as best as you can. And let's see if you can graph this next linear equation. We'll call this a classwork here. So classwork number 1. All right, classwork 1, I want you to graph y. I want you to graph x plus 2y equals 5 using these values for x. I want you to use the values of -1, 0, and 3. So you can make yourself a little table here. All right, ladies and gentlemen, you go ahead. See if you can come up with these 3 ordered pair solutions. Plot them in the XY plane to the best of your ability and put a line through those points. Let's graph this linear equation using the table method. Go ahead and do that. Classwork number 1. Alright, so these are the ordered pair solutions that you would generate when you let x be -1, 0, and 3. It's a matter of just plugging in the value in for x in the equation, and then solving the equation for y. So when x is -1, put -1 in for x right here. Then to get y by itself, you have to move the -1 over to the right side by adding 1 to both sides. And then to get y by itself, you have to get rid of this factor of 2 that's being multiplied by y by dividing both sides by 2. And you get y is equal to 3. -1, 3 would be one ordered pair solution to this linear equation in x and y. Then we let x be 0. Put 0 in for x. And now we have to solve this equation for y. Well, 0 plus 2y is 2y. To get y by itself, we divide both sides by 2, and we get y is equal to 5/2, which for plotting purposes is more conveniently represented as 2.5. 2.5. 0, 2.5 is another ordered pair solution to this linear equation. Finally, we let x be 3. Put 3 in for x, and now we have to solve for y. Since this is a positive 3, the inverse of addition is subtraction. So to move the 3 over to the right side of the equation, we subtract 3 from both sides. 3's drop out on the left, leaving you with 2y. 5 minus 3 is 2 on the right. Divide both sides by 2 to get y by itself, and we get y is equal to positive 1. 3, 1 is yet another ordered pair solution to that linear equation. Did anybody crank out those ordered pair solutions correctly? Anybody? Now what I need to do is plot these points in the XY plane. Taking a piece of graphing paper, I will do so. X-axis, Y-axis. Tick marks we will assume are 1 unit apart on both axes. All right, how do we plot our solutions? -1, 3. Start at the origin, I move 1 to the left and up 3. 1, 2, 3. There's -1, 3. The other solution is 0, 2.5. Start at the origin, stay on the y-axis, go up 2.5. 1, 2.5. Right there. 3, 1. Start at the origin, move 3 to the right on the x-axis. 1, 2, 3. Now up 1. There's 3, 1. Does it appear those points lie on a line? The answer is yes. Take a ruler, put a line through those points, and you have the graph of that linear equation in x and y. This is the graph of x plus 2y equals 5. That's its graph, and we're done. Any point that lies on this line will be a solution to that linear equation. Did anybody get that line for a graph?
Yeah.
Okay, got a question for you. Is this point here a solution to that linear equation? Is this point a solution to y, x plus 2y equals 5? Yes, because it lies on the graph. Would this point up here be a solution to my linear equation? X plus 2y equals 5. No, because it does not lie on the graph of that linear equation. Okay. Any questions on graphing linear equations using the this table method? All right. Now, ladies and gentlemen, there are 2 special cases for linear equations that I would strongly recommend that you just memorize. What would be the equation of a vertical line? The equation of a vertical line is always going to be just x equal to some real number c. You won't see the y variable in the equation of a vertical line, just x. And the graph of this equation is going to produce a vertical line that goes through the x-axis at c, whatever number c is. That'll be the graph of a vertical line whose equation always looks like this in general. Example, suppose x is equal to -3, and I wanted to graph this linear equation. Piece of cake. I know it's going to be a vertical line, and I know it's got to go through the x-axis at -3. There would be its graph. Makes sense, because any point that's on this vertical line could have any y coordinate. Do you agree? The y coordinate could be anything. But the x coordinate is always stuck at what value? Always stuck at -3. How about a horizontal line? What does the equation of a horizontal line look like? Well, it must always be in equation form y equal to some real number c. You won't see the x variable in the equation of a horizontal line. And the graph of this equation y equals c is going to be a horizontal line that goes through the y-axis at c, whatever number c is. This will be c. Example, y is equal to 4. What would be the graph of y equals 4? It's going to be a horizontal line that goes through the y-axis at, you guessed it, at 4. That would be its graph. And we're done. Those are two special cases. So just remember, just try to remember what the equation of a vertical line looks like and what a horizontal line looks like. Makes sense that the graph of y equals 4 is a horizontal line, because think about it, any point that lies on this horizontal line will always have a y coordinate that is 4. The x coordinate could be anything, but the y coordinate's always equal to 4. That's why its equation is y equals 4. Any questions about those? All right, there's another way to graph linear equations. We've seen the table method. Here's another method. It's called the XY intercept method. XY intercept method for graphing a linear equation. First of all, we need to define for you what an x and y intercept is for a linear equation. Suppose I have a linear equation, I graph it in the xy plane, and it looks like this. Now, the point of intersection between the graph of the linear equation and the x-axis, this point has a very special name, this point of intersection. It's called the x-intercept of the linear equation. X-intercept. And because an x-intercept must always be a point of intersection between the graph and the x-axis, it must always lie on the x-axis. And to be a point on the x-axis, the y-coordinate of such a point must always be equal to 0. Because if the y-coordinate of a point is not 0, the point will not be on the x-axis. It'll either be above or below the x-axis. This is the point of intersection between the graph and the y-axis. Therefore, this point is called the what intercept? Anybody want to take a wild guess if your life depended upon it? Not the x-intercept. It's called the
Y-intercept.
y-intercept. The y-intercept is a point of intersection between a graph and the y-axis. Therefore, y-intercepts must always be a point on the y-axis. And in order to be a point on the y-axis, the x-coordinate must always be equal to what for a y-intercept? The x-coordinate
0.
must always be equal to 0. Otherwise, the point will not even be on the y-axis. So, ladies and gentlemen, we're finding out rapidly how to even find x-intercepts. To find an x-intercept, we always set y equal to 0. To find a y-intercept, we always let x be equal to 0. And you know, this is not only true for linear equations, this is true for all types of equations in two variables, x and y. This is how you always find their intercepts, by letting the other variable be equal to 0. Hey, do you agree that if I can find the x and y intercepts, and they're two unique points, do you agree that's enough to what? Put a line through them and graph a linear equation? Isn't that true? All right, let's try one out. Let's try to find the intercepts. For this linear equation. Negative 2x plus 3y is equal to 12. We're going to try to find the intercepts for this linear equation and then graph the linear equation. Okay. So how do we do that? Now, does it matter what intercept you find first? The answer is absolutely not. I'm going to find my x-intercept first. What do I set equal to 0 always to find an x-intercept? What variable always gets set equal to 0? The other variable, y. Take 0, substitute it in for the y variable into the equation, and then we'll be able to solve the equation for x. So here we go. In for y goes 0. Therefore, our equation collapses down to negative 2x plus 0 equals 12, which is better known as negative 2x equals 12. How do I get x by itself? How do I solve this equation for x?
You divide by 2.
Divide both sides of the equation by a negative 2, correct?
Yes.
Negative 2 divided by itself, as anything divided by itself, reduces down to 1. And 1 times x is better known as just x. And that's what we wanted, x all by its lonesome. That's how we solve an equation for x, is to get x by itself. Now our solution's on the other side. What's a positive divided by a negative?
A negative.
It'll be a negative 6. 12 divided by negative 2 is negative 6. So my x-intercept for this linear equation is negative 6. Or as an ordered pair would be what? Negative 6 comma 0. That's the x-intercept. It's at this point where the graph of this linear equation is going to cross the x-axis at that point. Let's now find the y-intercept. What do I always set equal to 0 to find the y-intercept?
X.
The x variable. Take 0, substitute it in for the x variable into the linear equation, and then solve the equation for y. Upon making the substitution, my equation becomes negative 2 times 0 plus 3y equals 12. Negative 2 times 0 is as good as gone. That's 0. That's gone. And we're left with 0 plus 3y, which is just 3y, equal to 12. How do I solve for y now?
You divide by 3.
Divide both sides of the equation by 3. The left side simplifies to 1x or x. The right side is our solution, which is 12 divided by 3, which is 4. My y-intercept is 4, or as an ordered pair, it is 0, comma 4. That's your y-intercept. It's at this point on the y-axis that the graph of this linear equation will go through at that point. Ladies and gentlemen, any questions how I found the x and y-intercept for this linear equation? Do we have enough information now to use those two unique points and graph this linear equation? We got enough info, do you think?
Yes.
We got two unique points. That should be bare minimum good enough. Take a piece of graphing paper. We're going to plot the intercepts and put a nice line right through the center of those points. Label your axes always. All right, now let's plot the x-intercept, which is negative 6, 0. Starting at the origin, I move 6 to the left on the x-axis and stay on the x-axis. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. There's negative 6, 0, my x-intercept. We will plot the y-intercept, which is 0, 4. Starting at the origin, we stay on the y-axis and go up 4. 1, 2, 3, 4. There's the y-intercept, 0, 4. Take a ruler, put a nice, neat line through the center of these two intercepts, and you have the graph of that linear equation. It's that simple. Make sure you always put arrows on the end of your line. Ladies and gentlemen, that's the graph. That is the graph of my linear equation, negative 2x plus 3y equals 12. That's its graph. This method was called the what method? Not the table method, but it was called the XY intercept method for graphing a linear equation. Did that method make an ounce of sense? You think with practice you might be able to do something like this on Alex, maybe? Hey, you get to use the graphing tool on Alex. Isn't that cool? That's going to be exciting. Get to plot points and draw lines with the graphing tool. Isn't that cool? All right. Well, a whole bunch of fun awaiting us. Uh-oh. Time check. 1:25. I have a question for you, ladies and gentlemen. Do I have any downhill skiers in here? My other two sections had at least one downhill skier in class. Do I have any downhill skier in here? Anybody do downhill skiing? Well, let's assume that somebody does, okay? You know, the unhip way of saying let's go skiing this weekend is to say, hey, do you want to go skiing this weekend? The cool way of saying that is, hey, how about you and me hitting the slopes this weekend? That's a cool way of saying, you know, do you want to go skiing this weekend? Anybody ever hear that before? Let's hit the slopes. Because, ladies and gentlemen, to do downhill skiing, you need some sort of a what? A hill or a slope. Do you agree? Because if you don't have any hill or slope, ladies and gentlemen, you're not going to be doing any downhill skiing. Can you do any downhill skiing on a level surface where there's no slope or slant to it? No. You're going to be doing cross-country skiing, which is a lot more difficult than downhill skiing. But it's a lot safer than downhill skiing, though. Sonny Bono. Anybody ever hear of Sonny and Cher? They were a popular duet back in the 70s. You can show how old I'm getting here. But Sonny Bono, he was skiing out in California and he ran right into a tree, got killed. I think he was going about 70 miles per hour. Be careful with downhill skiing. Start with the bunny hill first and build yourself up gradually. Oh, and you might want to know where the brakes are on skis too. Always know where the brakes are. All right, ladies and gentlemen, how did I get on that topic of skiing? Well, because now we're going to address the issue of the slope of a line. Slope of a line in the XY plane. All lines have different slants to them or different slopes to them in the XY plane. We're going to develop a formula that's going to show you how to compute the slope of a line in the XY plane. Suppose I have some linear equation and I graph it in the XY plane, and suppose the graph of that line looks like this. Now I'm going to choose two unique points on this line. This point here is going to be the point called P sub 1. This is called a subscripted variable, P sub 1. This is the subscripted variable P sub 2. Because the subscripts are different, these are different points. They're not the same, they're unique. The ordered pair address of this point is going to be X sub 1, Y sub 1. The ordered pair address of this point is going to be X sub 2, Y sub 2. Your author in your textbook makes use of subscripted variables just like I'm using right here. If I project this point P sub 1 vertically down to the x-axis, what tick mark do I strike down here? What tick mark do I strike? Well, what's the x-coordinate of this point? Oh, it's X sub 1. In a similar fashion, if I project this point vertically right back down to the x-axis, I strike what tick mark value? Oh, what's the x-coordinate of this point? Oh, it's X sub 2. If I take this point and project it horizontally back to my y-axis, what tick mark do I strike? What's its y-coordinate? Oh, it's Y sub 1. Finally, if I take this point, project it horizontally back to the y-axis, I strike what tick mark value? Well, what's its y-coordinate? Oh, it's Y sub 2. Now we understand this picture so far. All right, ladies and gentlemen, I can build a right triangle in here. Does anybody see a right triangle in here? A little right triangle? See that there? All right, we need a mountain climbing yodeler. Here's a mountain climber going to be going up this line here, walking from point P1 up to point P2 along this line. You know, whenever I do this derivation, I think of that game on the Price is Right. You remember that little mountain climber that yodels as they go up that little slope, and the key is to try to prevent that person from falling off the cliff. And if you do, you win a bunch of prizes.
Yes.
Now, that's what this reminds me of when I go through this derivation. And so we got this yodeler going up this line, this yodel, you know what I'm saying? Climbing up the line. That's the best I can yodel, ladies and gentlemen. Now, when this person crawls up this line from point P1 to P2, two things are going to change. They're going to experience a horizontal change in their position, and they're going to experience a vertical change in their position as they go up along this line. So in a crude sense, ladies and gentlemen, the slope of a line is a ratio. It's the ratio of the amount of vertical change to the amount of horizontal change that you experience when you move from one point to another point on a line. We like to call it the ratio of rise to run. Rise is the vertical change, run is the horizontal change. But this is not mathematically accurate enough. This tells us diddly. We want to develop a precise formula that can help us compute the exact slope of this line here in the XY plane. So when we say rise, what do we mean more precisely? Well, the amount of rise we experience as we move along this line from P1 to P2 is going to be represented by the difference in the y coordinates, namely y sub 2 minus y sub 1. That's going to be the amount of vertical change. Y sub 2 minus y sub 1. That is the amount of rise we experience precisely. Precisely speaking, what amount of run do we experience in going from P1 to P2 along this line? That's going to be represented by the change in the x coordinates of these 2 points, P1 and P2, or x sub 2 minus x1. X sub 2 minus x1 therefore represents the amount of run, or the amount of horizontal change you experience as you move from point P1 up along the line to point P2, or vice versa. You could go along the line from P2 down to P1. It'll still be the same ratio. Ladies and gentlemen, we have developed a very important formula here. This is called the slope formula. And in all the textbooks that I've ever seen, pre-calculus, trigonometry, calculus, differential equations, advanced calculus, doesn't matter. They always use M for the slope. Why? I have no idea, okay? But they always use M. And M represents the slope of a line. And the slope of a line can always be found as taking the difference between the y coordinates of two unique points on a line and then putting that over the difference between the x coordinates of the two unique points on the line. This is called your slope formula. It will enable you to crank out the slope of any line in the XY plane, just so long as you have two unique points on the line to work with. Very important formula there. You might want to memorize that or have that handy on a note card somewhere before you sit down with Alex. It's called the slope formula. Okay. How do we use it? Well, let's find out. Suppose I want to find the slope. Oh, make sure when you spell the word slope, you put an E on the end, because if you don't, it's going to look like slop. Okay? Slope, not slop. Find the slope of the line that contains, suppose, the point of 2, 3 and 5, 8. I want to compute the slope of the line that contains these 2 points. How do we do it? Later on, we're going to use our what formula? I'll give you a hint. We're going to use our slope formula. Now, does it matter which point? Does it matter which point I call my x1, y1, x2, y2, y1? Does it matter which point I call my second point? point. Think it's gonna matter which point I call my first and second point? Nope, it's not gonna matter. Suppose I designate this as being my point x1, y1. And I designate this as being my point x2, y2. Using these points, let's compute the slope of the line that runs through these points. Here we go, slope formula. M slope is equal to, what's y sub 2? It would be 8 in this case. 8 minus what's y sub 1? 3. Over the change in x. X sub 2 is 5. Minus x sub 2 is, wait a minute. This should be x sub 1. Sorry about that. X sub 2 minus x sub 1. Y sub 2 minus y sub 1. X sub 1 would be 2. So the slope of this line is going to be 5/3. 5 is the rise. 3 is the run. Any questions? Aren't we curious to see exactly what this means geometrically speaking? Well, we can find out. We just take a piece of graphing paper and let's plot these 2 points and put a line through them, and let's see why it's a rise of 5/3 for the slope of this line. Y-axis, x-axis. Let's plot these points here. 2, 3. Start at the origin, move 2 to the right, up 3. 1, 2, 3. 2 to the right, 1, 2, 3. There's 2, 3 right there. Now we plot the point 5, 8. Start at the origin, 5 to the right, 1, 2, 3, 4, 5, up 8. 1, 2, 3, 4, 5, 6, 7, what? 8. Put a line through the center of these points, ladies and gentlemen. You have the graph of that line that contains those 2 points. Now, why is it a slope of 5/3? Suppose I start at this point and I walk from this point along the line up to this point. How much rise do I experience? My rise is going to be in the positive y direction. 1, 2, 3, 4, 5 units of rise. Plus 5 is the amount of rise. How much run do I experience? My run's going to be in the positive x direction. 1, 2, 3. 3 positive units of run. Slope is 5/3 for this line. Do we see that? Suppose, on the other hand, my mountain climber wants to go from this point down to this point. Suppose they want to walk the other direction, from here down along the line to this point. How much rise do they experience now? Well, now the rise is in the negative y direction. -1, -2, -3, -4, -5. How much run do they experience? Now the run is going to be in the negative x direction. -1, -2, -3. So I claim that the slope of 5/3 is equivalent to -5 over -3. Do we agree with this here? These are equal. So it doesn't matter if you choose this as your first point, this your second point, or choose this as your first point and this your second point. It doesn't matter if you walk from this point up to this point or from this point down to this point. The slope in each case will be the same for that line. What if I start at this point, ladies and gentlemen, and if I have a rise of 10 and a run of 6, will it still be the same slope? A rise of 10 and a run of 6? Is this ratio still equal to these? Still equal. So if I start at this point, and if I go up 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, now 6 to the right, 1, 2, 3, 4, 5, 6. I'll be darned if I don't land on the same line. Because 10/6 is the same slope as 5/3. Is this making any sense here, ladies? By the way, never confuse slope with an ordered pair or a point on the line. The slope of a line is not a point on the line. The slope of a line basically just indicates how much rise and run we would experience if we move from one point on the line to some other point on the line. Time check. 1:40. I'm gonna let you in on a little factual statement, little factual secret here, Lizzo. Any linear equation that generates a graph that looks like this, we say that the graph is a rising line in the XY plane. Rising line. And rising lines always have positive slopes. So if the graph of a linear equation is oriented this way in the XY plane, it's a rising line, it must have a positive slope. We call it a rising line because as we progress from left to right in the plane, we're rising on the line. We're rising. As opposed to if you had a linear equation and the graph of the linear equation looked like this, ladies and gentlemen, is called a falling line. Because as you progress from left to right in the plane, you're falling on the line, you're not rising. Falling lines always have negative slopes, always. To say the slope is less than 0 is to say the slope is negative. To say the slope is greater than 0 means the slope is positive. Does anybody want to take a wild guess as to what the slope of a horizontal line is? What would be the slope of a horizontal line? Anybody? What would be the slope of a horizontal line? Remember, slope is rise over what? Run. What does a horizontal line not possess? Rise or run? A horizontal line does not possess one of these, rise or run. Which one does it not possess, rise or run? A horizontal line. Well, if you move from one point to another point on a horizontal line, you have nothing but run. There's no rise. And because there is no rise, the rise will be 0 in the numerator of the slope formula. And 0 divided by any non-zero real number is 0. So the slope of a horizontal line is always equal to 0. What do you think the slope will be for a vertical line now? Anybody? Want to take a guess? The slope for a vertical line.
Wouldn't it be undefined?
You are correct. The slope for a vertical line, because a vertical line has nothing but rise, but there's no run now, so we would be dividing a real number by 0. And anything divided by 0 is, you are correct, undefined. So vertical lines always have undefined slopes. Horizontal lines always have 0 slopes. Falling lines always have negative slopes, and rising lines always have positive slopes. It's wise to know that. So you can check your answers. If you graph something, you can check by virtue of the orientation of your line what type of slope it must have. Good to know that. All right, we're in the home stretch now. Okay. If a linear equation is in this form, ax plus by equals c form, we say that it's in standard form, ladies and gentlemen. Standard form. If I took the time and did algebra on this equation and solved it for the y variable in terms of x, I could hammer this equation into yet another extremely important form. Y equals mx plus b form. Has anybody ever seen this form before for a linear equation? Anywhere. This is a very important form for linear equation. This, ladies and gentlemen, is called slope-intercept form. It's an extremely popular form for a linear equation. I'll tell you why. Because from the equation, we can just read off the slope of the line without doing any calculating whatsoever. The slope of the line is just a number being multiplied by x. That's your slope. So we can tell just by looking at the equation whether the line is a rising line, falling line, horizontal, or vertical line. This number B here is called the y-intercept of the line. It's where through the y-axis the graph of this line goes. That's why they call this the slope-intercept form for a linear equation. Extremely useful form. You see this word slope, ladies and gentlemen? Slope is really a rate in mathematics. It's a rate. It's a rate of change of y with respect to x. Can anybody else give me an example of some rates that are actually in existence in the real world? A rate. Can anybody give me an example of a rate in the real world? Example of a rate.
What do you mean, like miles per hour?
You got it. That's a beauty. Miles per hour. This is called a rate. Anytime you see the word per, miles per, anytime you see the word per, you're always talking about a rate. Miles per hour is a rate. It's the rate of change of distance versus time. It's called a rate.
Like
Can you
dollars
imagine-
per hour.
What's that?
Dollars per hour.
Yeah. Dollars per hour. This would be your pay rate. Do you agree? That's why they call it a pay rate, because it's a rate. It's a dollars per hour. That's a pay rate. Any other examples of any rates out there? I got one. If you get on your computer keyboard and type in, let's say, so many words.
Words per second?
Well, in my case, it's words per hour.
Minute.
Words per hour. So I'm too embarrassed to mention words per second in my case. Well,
Words per
normally
minute?
normally it's words per minute in like typing school or whatever. That's a rate, ladies and gentlemen. That's the rate with which you're typing on your keyboard. Words per minute. So all of these are rates. So whenever you see the word per, you're talking about a rate. Well, guess what? Slope is a rate. Slope is the rate of change of y per change in x. Okay? And we're going to find out the importance of the slope being a rate when we get into application problems, which is right around the bend. Okay? So ladies and gentlemen, we're going to touch base with and study this a little bit more in detail, this very important form called slope-intercept form for a linear equation. Slope is a rate. You know what the y-intercept is? Usually the y-intercept is like the initial amount of something, or the initial value, or amount of something, okay? Or like a starting value of something. Slope is the rate, all right? Slope is a rate of change. And you really put rate of change or the slope under the microscope when you get into your first semester of calculus, when you start working with the concept of a limit and you start ramping up to something called the derivative in calculus, the derivative of a function, and that's called differential calculus. A derivative is an instantaneous rate of change of one variable with respect to another variable, okay? So I give you a little snippet of calculus, gave you a little extra for your money. Isn't that cool? Hopefully that made somebody hungry out there, hungry for more math. All right, ladies and gentlemen, let's try some out here. Suppose I give you this linear equation here. I got a question for you. Is this linear equation in standard form or slope-intercept form? What form is it in?
Slope intercept.
Yeah, it's in slope-intercept form. It's in the form of y equal to mx plus b form. Being the case, what is the slope of this line? I should be able to read it right off from the equation. What is it?
2/3.
It's 2/3. So we have a rise of 2 and a run of 3 as we navigate from one point on this line to some other point. That's the ratio of the change of our vertical position versus our horizontal position. What's 7? The 7 is called the y-intercept. Or as an ordered pair, it would be the ordered pair 0, 7. This is where through the y-axis, the graph of this linear equation will go. It'll go through the y-axis at 2/3 x plus 7. Okay, 2/3 x plus 7. That's called the y-intercept. All right, here's another one. Very good. Is this linear equation in slope-intercept form? Yes, it is.
No,
What's that?
I said no.
Well, technically, it's not until you do this. Now is it in slope-intercept form?
Yes,
Yes, it is. What will be the slope? The slope of this line,
-1/5.
-1/5. And do you agree that you could represent -1/5 like this, or you could represent it as -1/5, or you could represent it as 1/5? Aren't these all equivalent? They're all equal to each other. Do you agree? So whether you go from one point to another point, you go down 1 unit and 5 to the right, or if you go up 1 unit and 5 to the left, you'll still be landing on the same line. So what is the slope of my line here? Oh, it's -1/5. What's my y-intercept?
0.
0, or as an ordered pair would be 0, 0. And this point 0, 0 has a special name. It's called the what of the XY plane. It's called the origin. So the graph of this linear equation will literally go right through the origin, will contain the point 0, 0. All right, let's go have a little bit of fun in our textbook now, ladies and gentlemen. We've earned it. We've matured enough where by now we can appreciate some of these problems coming out of our textbook. So we're going to go to our textbook in section 6.3, and we're going to have some fun. How many people actually look over the sections of the look over the sections in the textbook that I discuss? How many people take the time to actually do this? Well, I tell you, this is a wise thing to do, Liz. I've been harping on it throughout the entire semester. It only can reinforce what I'm talking about. Okay. So please do take the time and, just kind of look maybe down through some of these examples, or if you want to read the section verbatim, go ahead and do that. Okay, that's just more power to you. Okay, hey, look at a nice job they do here. Do you know roads have slope to them too? Roads have slopes. Well, they don't call them slopes in the road industry. They call them grades. Grade, grades. Have you ever been driving in the mountainous areas and ever see a sign that says, slow down, steep grade ahead? Steep grade ahead. That means there's a very fast, there's a very large hill ahead. And you might want to slow down, because if you don't slow down, especially if there's snow or ice on the roads, you're in for one heck of a ride. Do you agree? Truck drivers have to pay attention to grades of the road. Diesel locomotive engineers have to pay attention to grades of tracks in the mountainous areas, because if they don't pay attention to them, if they don't apply proper braking, they can have what's called a runaway. And a runaway is a bad thing. Okay. So roads have slope to them, ladies and gentlemen. It's called the grade of the road. All right. Roofs have slope to them, but they don't call it slope in the roofing industry. They call it the pitch of the roof. What kind of pitch a roof has. Pitch is the same thing as slope, though. Some roofs are steep, some are not steep. Does this road have any grade to it, ladies and gentlemen? Any slope? Doesn't look like it. This road kind of looks like the road that Forrest Gump ran along. Do you agree? That looks like the road Forrest Gump ran around. Kind of looks like it, doesn't it? Look at this. they got the derivation of the slope formula in color. I tried to derive it without color. Well, I'll tell you, you gotta love this book. All right, where are we going with this? Well, I want to do some problems. On page 326, example 10. I want to go over this problem here. Look at it's in color too for us. I could never duplicate this on my paper. A standard fare for a taxi in one city is $5.50 plus 30 cents per mile. Write a linear equation that describes the cost of a cab ride in terms of the length of the ride in miles. Then use your equation to find the cost of a 6-mile ride, an 8.5-mile ride, and finally a 12-mile ride. All right, so how are we going to do this, Lizzo? Let me ask you this question here. I see two numbers in this word problem. One of them is the slope and the other one's the y-intercept. Which is which? How do you identify these numbers?
The 0.3 is per mile, which is the slope.
Yeah. Per, you got the word per here. That means this must be the what? This must be the slope. That number is the slope. So this must be the y-intercept then. So therefore, to write the equation of this line, here's the skeletal form for a linear equation in slope-intercept form. All we got to do is populate the slope and the y-intercept and we'll have our equation. So y is going to be equal to, what's my slope?
3/10.
Yeah, you could say 3/10. Or you can just leave it as 0.30 if you want. It's okay. 30 cents per mile times X miles, correct? Plus, what's the one-time fee you got to lay out for just stepping into the cab?
$5.50.
$5.50, whether you go 1 mile or go 100 miles in that cab, you're going to be paying the $5.50 guaranteed. That's called a fixed cost. The variable cost is the 0.30 times X. That depends upon the distance or the length of ride you take in the cab. Ladies and gentlemen, this would be the linear equation that models this cab fare, where Y represents the what? The cost in dollars of the cab ride. And what do you think X represents?
The length of the ride.
Yes, the distance that you go in the cab, the number of miles you ride around in this cab. There you go. And you have a linear equation that basically embodies the relationship between these two variables, X and Y. The larger X becomes, the greater the cost becomes. Do you agree? Now we can use this equation to answer some of these questions. If I take a 6-mile ride, that means I got to let X be equal to 6 miles. I would take 6 and then I would plug it into my what equation? So Y is equal to 0.30, 30 cents per mile times 6 miles. Get on your calculator, ladies and gentlemen. Plus 550. Get on your calculator and dial this up. Tell me how much it costs to go 6 miles in this cab. I got to see if I got enough money here to get home.
$7.30.
$7.30. If you go 6 miles, do you agree? Everybody understand this problem here? How I transform these words into a linear equation and then use that linear equation to answer some questions? Classic application problem of a linear equation here. Any other questions about this? This is example 10 in your book. It's there for your viewing, in case you didn't get any of this. It's all there. Oh, what am I saying? This is being recorded anyways. But there you go. See, it's all here. They even do the other ones, for a 12-mile cab ride, it's going to cost you $9.10. 8.5-mile cab ride, it's going to run you $8.05. All right, let's try another one. Problem number 70 on page 329. So on page 329, we're going to try problem number 70. In fact, ladies and gentlemen, I'm gonna have you do this problem for classwork. We'll call this classwork number 2. A house painter charges $60 for a home visit and $210 per ding 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 per room painted. Write an equation, a linear equation that describes the cost of hiring the painter in terms of the number of rooms that will be painted. Then use your equation to find the cost of painting a house that has 5 rooms, or 7 rooms, or 20 rooms. You know, so we're all on the same page. I want everybody to use Y to represent the what? The total cost in dollars. And I want X to represent what? What do you think X should represent? Anybody? Are we talking about distance here?
Rooms.
No. It's the number of what?
Rooms.
Number of rooms that are painted. Yeah. All right, go ahead. I want you to build a linear equation that models this word problem. And then I want you to use it to answer, you know, maybe at least the first question. How much a 5-room house is going to cost? We'll call this classwork number 2. Okay, did anybody come up with the equation that looks like that?
Yes.
Y $210 per room times X rooms plus $60, correct? And if you have this painter paint 5 of your rooms, it's gonna cost you how much? $1,110, correct? I got a question. What if the painter comes out, looks at your house, and gives you their price quote as to how much they charge per room, and you say, no, I'm gonna shop around? Do you still have to pay this person some money for that trip out to your joint?
Yes.
Oh, you bet you gotta pay him some money out. You still gotta pay him $60. Do you agree? Just for coming out. That's just to come out. All right. They probably charge us maybe just for maybe gas money or something like that. I don't know how far they have to drive or something. It's called a fixed cost. This covers their rear end. Because stop and think, Liz, I mean, if you're in that business, wouldn't it be a drag if you drove all the way out to some place? Maybe you had to drive 200-300 miles, and then they turned you down and said, no, I don't want you to paint any of my rooms. Can you imagine that, going through all that hassle of driving all the way out there, wear and tear and gas? You'd want some money too. Do you agree? That's why they got that fixed cost out there. All right. That's number 70 on page 329. That's a classic example. All right, let's try to take a look at another one here. Number 83. It says Saudi weighs 160 pounds, but has started a new diet plan that promises a loss of 3 pounds per month, every month, until reaching a goal weight. Write a linear equation that describes how much Saudi weighs each month, and then use your equation to find how many months it will take to get to 130 pounds. I'll tell you, the easiest part of this problem by far is writing the equation. The tougher part is answering this question. How many months is it going to take to get to 130 pounds? I'm going to let you play around with this, ladies and gentlemen. Classwork number 3. See if you can write the equation. Let y be equal to the what? Weight. And let x be equal to the number of months on this diet plan. Y equals weight in pounds. X equals number of months on the diet plan. Go ahead, do number 83. All right, first of all, did we get the equation written down correctly, if nothing else? Y is equal to negative 3x plus 160. The slope is losing 3 pounds per month. That's a rate. It's the rate of weight loss per month. It's negative because you're losing weight. If you're putting on weight, this would be a positive, but this slope's got to be negative. This is the original or the initial what? Weight. That's your y-intercept. Did anybody get this equation correct? If nothing else, are we on the right track here? Because if you don't have the correct equation, there's no hope, correct? All right, now they want us to answer the question. Using that equation, they want to know how many months must we be on this diet plan in order to get down to 130 pounds of weight. So I have a question, ladies and gentlemen. Where do I put 130 pounds? Do I replace the X variable or the Y variable with 130 pounds?
Why?
Why? Because that's what Y is declared to be, the weight in pounds. So we let Y be 130 pounds. And now we have to solve this equation for X to determine how many months we must stay on this diet plan. How do we solve for X here? How do I get X all by its lonesome on the right side of this equation? What do we do first?
Subtract 160 from each side?
That's right. We got to bring the constant 160 over to the left side to join 130. Since it's a plus 160, to move it to the other side of the equation, we have to use the inverse operation of addition, which is to say we subtract 160 from both sides. 130 minus 160 is negative 30 equals negative 3x. And the 160s on the right side drop out to 0. They're gone. Now, how do I solve for X? How do I get X by itself?
Divide.
We divide both sides by what? Negative 3? Okay. All right, now negative 30 divided by a negative 3, a negative divided by a negative is a what? Positive, so it'll be positive.
10.
And this is what? Just X, correct? 1X. These reduce down to 1. So how many months must we stay on this diet plan to get down to 130 pounds?
10.
10 months, and we're done, ladies and gentlemen. Is this making sense here? Using linear equations to model real-world situations. Pretty neat, huh? Pretty cool.
I'm
I
able
think,
to.
I think that's where the beauty of math lies, is being able to apply it to, you know, the real world. At least that's, in my estimation, the real beauty of math. But there are people that would argue opposite of what I just said there, though. So, all right. So I think that we went through enough here, ladies and gentlemen, in section 6.3 for you to get the idea as to what's going on here. I think that you'll have success. So I will open up the chapter 6. I will open up 6.2 homework and 6.3 homework on Alex. I'll open up the chapter 6 quiz and the chapter 5 and 6 exam. Just got to keep your eyes on these due dates here. Very important, okay? If there are no other questions, you have a great weekend. I'll stay on the line for a couple minutes if you have any concerns or anything. All righty, take care.
Thank you.
We'll see you. Have a good weekend.
Have a good weekend.